In the last video, we introduced a simple linear regression model, and we used the example of a study of 32 male lions in Tanzania, and we established a linear relationship between the proportion of black pigmentation on the lion's nose and the age in years. And so just to remind you, we came up with an equation for this regression line here that had a y-intercept of 0.879 and a slope of 10.6471. So let's look at a few other aspects of this fitted model. So when we were talking about the study, we talked about how the researchers were hoping to come up with a model that would allow them to predict the age of a lion based on the proportion of black pigmentation on the lion's nose. And so one way to do that is as follows. So for example, let's suppose the researchers have measured the amount of black pigmentation in a particular lion, and they've discovered that it's 0.5, so 50% black. Using this fitted simple linear regression model, what would be the predicted age for that lion? So we can do this kind of longhand. So remember, A was the estimated intercept, and then B was the estimated slope. And so we could use the regression model equation to predict the value of age at proportion black equal to 0.5. So the way that we do that is just by using this formula, and we end up with what I'm calling y hat. So y stands for the response variable, and the hat means that this is an estimate or a prediction. And so we can see that the predicted age for a lion with 0.5 black pigmentation, a proportion of 0.5 black pigmentation on their nose, would be predicted to be 6.2 years old. We can also use this built-in function here. And if we want to get a little more help on this type of function, you'll see once you start typing predict into this help search function, there's a whole bunch of different types of prediction, and the one that we're going to do is predict.lm because we fit a linear model, and that was the code that we used when we fit the model up here, lm. So if I select that, it will tell me what the predict method for linear model fits is actually doing. So there's a lot of information here. This can be a little bit tricky to use, this function, because this second argument, new data, if we want to make a prediction at a particular value of the predictor, we need to put it in this form like this. So we need to use this syntax here, data.frame, and then this is the name of the predictor, and then an equal sign, and then this is the value that we want to make the prediction at. So if I run that code, we're going to get the same answer that we got when we did it kind of by hand. So it's probably a little better to use this method because this is more general. When we go on in a future lesson to talk about multiple linear regression, we're going to have multiple predictors, and it's going to be very cumbersome for us to write out the prediction using this method here. Much easier if we can just use this built-in function predict and make the prediction that way. So that's a prediction, and we can kind of look at the graph to make sure that it makes sense. So we're predicting at x equal 0.5. So if I go up to the regression line at 0.5 and then across to the age axis, apparently that value is 6.202566 according to the prediction that we just made. So that seems to fit with what the graph looks like. So those are predictions. I mentioned residuals in the last video, and so the residual for any sample observation, if let's take this one, say the actual age, the observed age of this lion is given by this position here. So looks like it's about 7 maybe for this lion, whereas the prediction for this lion is, well, it looks like the proportion black for this line is 0.5, and we just figured out that the prediction for that line is 6.2, and so the residual would be the difference between 7 and 6.2. So the residual for this lion would be 1.2. So we can calculate the residuals for any of the sample observations, and so this would be one way to do it. And again, we could calculate y hat first, and then calculate the residual as the observed response, which is this piece, minus the predicted response that we just calculated. So we get minus 0.49 for the 31st lion in the data set, which I'm guessing is, well, I don't know, maybe it's that one. Let's look at the proportion black for the 31st lion. Just got to highlight the right piece. So it's 0.79. So yeah, it's this line here. So we can see that that is a negative residual because the point is below the line, and it's minus 0.49 that it comes to. The other way of doing it, we could use the predict function again and then to get the prediction, but we could also use the resid function to calculate the residual directly. And again, it's probably better to use these inbuilt functions than to try and kind of do it longhand like this. So those are residuals. If I want to look at the residuals for the entire sample, I can apply this function to the fitted model. So if I run this code, I'll get a list of 31 residuals. So there's all the, sorry, 32, there's 32 lions here. I get a list of 32 residuals. And if I take these residuals and square them and then add them up, so that would be using this code here, the sum of the squared residuals, then I get this value here, 83.54321. So remember when we talked about how the regression line is fit, it's using the idea of least squares. So it's the line that produces the smallest value for the sum of squared residuals, or the residual sum of squares. And that particular value for this model, for this example, comes to 83.54. The sample size here is 32, and so the degrees of freedom for the residuals is equal to n minus 2 for a simple linear regression model. So n is 32, and so 32 minus 2, the degrees of freedom is 30 for this example. If I take the residual sum of squares and divide it by the degrees of freedom for the residuals, I get a quantity known as the mean square error. So that's 2.78474 in this case. So this is typically called the mean squared error. It can also be referred to as the residual mean square. So you'll hear both of those terminologies used. So we can then use that mean squared error or residual mean square, and we can calculate the standard error of the slope. So that's what I'm doing here. If I take that mean squared error or residual mean square and divide it by, so sx2, what is that? So let's go back up and find out what that is. That's this quantity here. So if I do that calculation, then take the square root, I get something called the standard error of the slope. But it's, if we remember back to the summary that we looked at in the last video, here was the estimated intercept, here was the estimated slope. In the column to the right of the estimates is something that's labeled standard error. And so this is the standard error for the intercept, and this is the standard error for the slope. So that's the number that we're calculating here, the standard error of the slope. So 1.5095. And we can use that to calculate a confidence interval for the slope. So the way that the confidence interval is calculated, it follows the usual format. We have an estimate in the middle, and then plus or minus a critical value times a standard error. So if, for example, we're wanting to do a 95% confidence interval for the slope, if our significance level is 0.05, then the critical value that we want is going to be the 97.5th percentile of, in this case, a t-distribution with degrees of freedom equal to n minus 2. And why the 97.5th percentile? It's because if you think of a 95% confidence interval, if we have a 95% in the middle, we'll have 5% evenly distributed between the two tails, so 2.5% in one tail, 2.5% in the other tail, and so that critical value that we need is going to be the 97.5th percentile. So it's the number that has 97.5% to the left and 2.5% to the right. So in this case, that critical value is 2.042272, and then we calculate our lower bound and our upper bound for the interval using the estimated slope, which is b, plus or minus the critical value times the standard error. So we get 7.564308 for the lower bound, 13.72993 for the upper bound. So going through these calculations, it's helpful when you're first learning about this topic, because it gives you a slightly deeper understanding of where the numbers are coming from. But in practice, as is often the case, there's a built-in function that will do these calculations for us without us having to remember the formulas and potentially making mistakes. So this confint function, if we run that, then we get our interval right there. So that's the interval that we just calculated by hand, and it's provided to us directly. So we can say we're 95% confident that the population slope is between 7.56 and 13.73. So we've looked at a few more details of the simple linear regression model. We've looked at predicted values, we've looked at residuals, we've looked at the residual mean square or the mean squared error, we've looked at the standard error of the slope, and then used that to help us figure out a confidence interval for the slope. And in the next video we're going to look at what are called confidence intervals for the mean, sometimes described as a confidence band, and we'll also look at prediction interval And so these concepts are related, but they're subtly different, and so we'll spend the whole of the next video looking at those two ideas.